Hello everyone, this is Miss Lindsay. Today we're going to talk about the second derivative test for concavity and locate the points of inflection. Okay, so let's recap what we already know from the previous sections. What we already know is increasing and decreasing open intervals. So we know it's increasing if we have the first derivative. If it is positive, so in other words greater than 0, that's when it's increasing, and it's decreasing when the first derivative is less than 0, so in other words negative. Now let's take a look at just a random graph, and let's compare the parts of this graph here. Okay, so what's the difference between the blue parts of this graph as well as the red parts of the graph? Hopefully you're saying to yourself here, in red, this is where it's opening up. So it opens up. And in the blue, it's opening down. So it opens down in the blue, opens up in the red. So if we actually take this exact same graph, what we can talk about with these is concavity. Concavity is the property of curving upward or downward. So this exact same graph, which we talked about on the previous screen, the red portion was opening up, so in other words that's concave up. So we could say the interval of this first one is going from negative infinity to negative 1.5. So again, I'm just estimating that right there. Then the other portion would be going, I'm going to call that 0.5, even though it doesn't quite look like that. 0.5 from here all the way to 2.5. And then we have it concavity going down. So again, we have this portion here. So again, I'll say that is from negative 1.5 all the way to 0.5. And then again from 2.5. to positive infinity. So again, we're describing with our intervals the portions where it's opening up and where it's opening down. So an interval is said to be concave up when the first derivative is increasing, and it's said to be concave down when the first derivative is decreasing. So a really good way to think about this is it is concave up if the part of the graph that lies above the tangent line, and it's concave down when part of the graph lies below it. So in other words, if you kind of take a look at this, so here I have my horizontal tangent lines, or here, so it is concave down when the portion of the graph is below the horizontal tangent lines, and here if I have a horizontal tangent line, I didn't draw that one very well, but there and there. And again, that is where it lies, the part of the graph lies above the horizontal tangent line. Okay, so that's just another way to think about those concave up and concave down. Okay, so how do we test for concavity? Now we are going to actually find the second derivative. Notice there's two little tick marks there. So we're talking about the second derivative test. Second derivative. So find where the second derivative is 0 or undefined. These x values will determine the test intervals, and then again we will take the second derivative and we'll test the sign for each of those intervals. So you're going to see it's very similar to what we did with increasing and decreasing intervals, but now we are using the second derivative test. So let's go ahead and try an example with this. So here we want to find the intervals of concave up and concave down for this function. So just like we started out with increasing and decreasing, let's go ahead and find the first derivative. So we're going to use our power rule to find the first derivative. But again, because we're finding concave up and concave down, we need to now take the second derivative. So again, going to use the power rule here. So multiplying and decreasing our exponent down by 1. So we found the second derivative, going back to the rules here, and now we're going to find, again, where is equal to 0 or undefined. So in this case, it'd only be equal to 0 because we are not working with a fraction there. So we'll set that equal to 0. Now we're using our algebra skills, simply solving this. In this case, we have a GCF that we can factor out of 20x squared. And then we're left with x plus 3. And set each of those equal to 0. So in this case, we get x equals 0 and x equals negative 3. Okay, so again, similar to what we did with increasing and decreasing intervals of the first derivative, we're going to find our number line. We're going to put our numbers, negative 3 and 0, on the number line, and we're going to plug this now into the second derivative. So I'm going to take something here. Let's say that I'm going to take negative 4, and I'm going to plug that into the second derivative. And again, it doesn't matter if it's really, we don't need to necessarily know the exact number. We just need to know if it's positive or negative. And since I plug in negative 4 here, I will get a very large negative number here. And I'll add it to a positive number because I'll square it there. So this is going to be negative. And then if we plug in a value in between, so I'll choose, negative 1. And then I'll choose a value above. So go ahead, pause, plug those into the second derivative and see if you get a positive or negative number. And you should have gotten a positive number when you plugged in negative 1 to the second derivative, and a negative number when you you should get a positive number, because both of these would be positive when you plug in a number greater than 0. So in this case, we have what we call a point of interest. That is going to be at negative 3. So here we have, it's negative, so that is going to be where it is concave down. And then it's going to be concave up because these are positive everywhere greater than negative 3. So this is our point of interest where we have something going from concave down to concave up. So this would be going down, and then these would be going up. Okay, so just kind of in general. So our concave down, I'll just write C with a little down arrow, it's going to be negative infinity to negative 3. And our concave up will be from negative 3 to positive infinity. And so again, we call negative 3 what we call, that does not look like a very good negative 3. Let me just go ahead and redo that one. Negative 3 is what we call our points of interest. And we'll expand on that in just a little bit. Because we can actually find what that point of interest is by plugging it in. Whenever we're finding the y value, whenever we're finding the y value, we always plug it into the original function whenever we're trying to find the y value. So this again here is going to be for the difference, so it's going to be going from where it's concave down to concave up. So if I plug it into g of x here, so I'd have negative 3 to the 5th plus 5 times negative 3 to the 4th minus this over. A little more room there. Minus 40 times negative 3. If I plug that in, I should get a value, it's a rather large one, of 282. So this would be our point of inflection. So again, what is this POI? Point of inflection. That is where the point goes between concave up to concave down and vice versa. And I'll, once you write this down, I will go back and show you exactly where that would be on our, when we first started talking about this with concavity. So let me go back to our original graphic this would be a point of inflection. This would be a point of inflection. That would be a point of inflection. Because again, it changes from concave up to down and vice versa. Okay, so let's talk about that just a little bit more. Go ahead and pause and write this down, and then we'll talk about it. So here we have point of inflection is a point where the concavity changes. So in other words, where the second derivative equals 0 or it's undefined. And again, make sure that concavity changes for it to be a point of inflection. So it's got to go from up to down or down to up. And it is possible that you could have a max or min at that C value. So let's kind of put together everything that we've been doing in terms of increasing and decreasing intervals as well as concavity and points of inflection. So recall from previous unit how to find the intervals for which f is increasing and decreasing. This is when we're going to use the first derivative, and then part B says find the intervals where it's concave up or concave down. That is where we're going to use the second derivative. So I'd like you to pause and do part A. When you're done, push play to check your answer, and then we'll continue on and do concavity up and down together. Okay, so you can see on the left here, I took the first derivative, factored to find my critical numbers here of 1 and 3. Again, plug that into your number line here to find increasing, decreasing. So if you plug in values, now you're plugging this into, so again, I would plug it into the first derivative to figure out if these are positive or negative to find my increasing, decreasing intervals. So now when we go to part 2, we're going to piggyback off of this first derivative. I'm going to take that first derivative, but now I have to find the second derivative. So the second derivative will be negative 6x plus 12. And we're going to go through the exact same process that we did to find increasing, decreasing, and the critical numbers there. So I set it equal to 0, and then I solve. So here I get a value, an x value of 2. And then I'm going to, again, make my number line here, test the value in the second derivative, which is above and below 2. So if I plug in 0, again, I'm plugging into the second derivative here. If I plug in 0, I get 12, so that'd be positive. If I plug in 3, I get negative 18 here, and I add 12, so that's going to be a negative number, negative 6, which tells us when it's positive, that is going to be concave up from negative infinity to 2, and it's negative, so it'll be concave down between 2 and infinity. So this tells us, if I move this down just a little bit further here, this tells us that we have a point of inflection at 2. So this is going between concave up to concave down, so our point of inflection is at 2. So to actually find our y value, we're going to plug that into our original function here. Okay? So to find my y value, I have to plug in f of 2. So f of 2, plugging that into my original function here. And I do my calculations. I get that to be negative 2. So my point of inflection is 2, negative 2. Again, that's where it goes from concave up to concave down. And this concludes our notes on concavity.